Linus Pauling's College Chemistry, published in 1954, represents a monumental achievement in chemical education, a paradigm shift that reverberates through classrooms and laboratories to this day. It moved beyond descriptive accounts of chemical facts, instead emphasizing the underlying principles of chemical bonding and molecular structure, profoundly influencing how chemistry is both taught and understood. The book's significance extends past its immediate impact, shaping subsequent generations of chemists and informing the development of more advanced theoretical frameworks. Pauling's approaching college chemistry contrasts sharply with the chemistry textbooks prevalent before the mid-20th century. Prior texts often presented chemistry as a collection of disparate facts about elements and compounds, largely devoid of unifying theoretical constructs. Students memorized properties and reactions, yet might struggle to grasp the fundamental forces governing chemical behavior. This descriptive, almost encyclopedic, style provided limited predictive capacity and hindered deep understanding. Texts such as A Textbook of Chemistry by William A. Noyes, while comprehensive for their time, focused primarily on empirical observations and lacked the emphasis on electronic structure and quantum mechanical principles that would characterize Pauling's work. These earlier books, while valuable, served more as repositories of chemical knowledge than guides to understanding the why behind chemical phenomena. Pauling, fresh from his Nobel Prize-winning work on the nature of the chemical bond, brought an entirely different perspective to chemical education. His book integrated quantum mechanics, resonance theory, and electronegativity concepts to explain and predict chemical properties. He presented the wave mechanical treatment of atomic structure, explained the formation of molecular orbitals, and thoroughly explored the concept of resonance, showcasing how multiple Lewis structures could contribute to the actual electronic structure of a molecule. Consider, for instance, Pauling's treatment of benzene, where he explained its exceptional stability and unique reactivity in terms of resonance between two molecular structures. This approach offered a far more sophisticated and insightful understanding than the solely descriptive accounts found in earlier textbooks. A cornerstone of Pauling's approach was his emphasis on electronegativity, a concept he had pioneered. He provided a quantitative scale for electronegativity and demonstrated how electronegativity differences influenced bond polarity and reactivity. For example, he elucidated the partial ionic character of bonds between elements with disparate electronegativities, such as sodium chloride, and explained how this ionic character dictates their physical and chemical properties. This approach replaced qualitative descriptions with a predictive, quantitative framework. Students could, for the first time, reasonably predict the behavior of a compound based on the electronegativity difference of its constituent atoms. College chemistry also introduced structural chemistry concepts to a mass audience. Pauling meticulously detailed molecular geometries, bond lengths and bond angles, using X-ray diffraction data, much of which he himself had gathered. His depictions of molecules were far more realistic and informative than the simplistic representations found in older textbooks. He showed, for instance, how the tetrahedral arrangement of bonds around carbon atoms explains the three-dimensional structure of organic molecules and discussed the subtle distortions from ideal geometries caused by steric hindrance or electronic effects. This focus on three-dimensional structure proved revolutionary, paving the way for a deeper understanding of molecular interactions and biological processes. The immediate impact of college chemistry was substantial. It rapidly became a standard textbook in colleges and universities across the United States and worldwide, eclipsing many of its predecessors. Instructors embraced Pauling's approach, incorporating his emphasis on electronic structure and bonding theory into their lectures and laboratory exercises. Students, initially challenged by the increased mathematical rigor, ultimately benefited from a more profound understanding of chemical principles. The book spurred a wave of curriculum reform, with other textbooks adapting Pauling's conceptual framework and pedagogical approach. The book's legacy extends far beyond its immediate impact on chemical education. It influenced the development of computational chemistry, providing the theoretical underpinnings for calculating molecular properties and simulating chemical reactions. Researchers continue to use Pauling's concepts of electronegativity and resonance to develop new materials and design novel catalysts. His insights into molecular structure have proven invaluable in fields such as drug discovery and materials science. Modern textbooks owe an immense debt to college chemistry, which set a new standard for clarity, rigor, and conceptual depth. Despite its profound impact, college chemistry faced certain critiques and limitations. Some instructors found its mathematical treatment daunting for introductory students. Others felt that it focused excessively on theory at the expense of practical applications and descriptive chemistry. These criticisms prompted revisions in subsequent editions of the book and the development of alternative textbooks that sought to strike a better balance between theory and experiment. A modern course might still cover concepts such as molecular orbital theory, however. Today it is often accompanied by extensive lab work and real-world cases. One specific point of discussion involved the presentation of molecular orbital theory, while Pauling introduced the basic concepts. A fuller treatment required more advanced mathematical tools. The complete solution of the Schrödinger equation for even simple molecules remained computationally difficult at the time. Certain simplifications and approximations were necessary. The theory, despite its power, could prove initially confusing for undergraduates attempting to grasp the intricacies of electron wave functions. Directly influencing the creation of college chemistry were the works of Gilbert N. Lewis, particularly his concept of the electron pair bond, and the early developments in quantum mechanics by scientists such as Erwin Schrödinger and Werner Heisenberg. Lewis' ideas about shared electron pairs provided a crucial stepping stone for Pauling's theory of resonance and electronegativity. The quantum mechanical framework developed by Schrödinger and Heisenberg furnished the mathematical tools necessary to describe the electronic structure of atoms and molecules. Pauling adeptly blended these concepts to create a unified and coherent picture of chemical bonding. One can easily view Pauling's work as a direct extension into the practical, testable field of chemistry. The theoretical concepts that came, conversely, college chemistry directly influenced generations of chemists, including Nobel laureates such as Roald Hoffmann and Robert Kurl. Hoffmann, in his work on molecular orbital theory and the Woodward-Hoffmann rules, built upon Pauling's foundation to develop a deeper understanding of chemical reactivity. Kurl, who shared the Nobel Prize for the discovery of fullerenes, acknowledged the profound impact of college chemistry on his intellectual development. The book also influenced textbook writers such as Theodore L. Brown and H. Eugene LeMay, whose Chemistry the Central Science adopted many of Pauling's pedagogical approaches and organizational structures. Consider the specific example of using resonance theory to describe the structure of ozone. O3. Pauling explained how ozone could be represented as a resonance hybrid of two Lewis structures, one with a single bond and a double bond between the oxygen atoms, the bonding switching to the other oxygen atom, within a second Lewis depiction. This representation accounts for ozone's observed bond length and stability, something a single Lewis structure fails to capture. This approach, propagated through college chemistry, became a standard method for understanding the electronic structure of molecules with delocalized electrons. Another example is Pauling's discussion of hydrogen bonding. Pauling explained that hydrogen bonds form between a hydrogen atom bonded to a highly electronegative atom, such as oxygen or nitrogen, and another electronegative atom. He detailed how hydrogen bonds influence the physical properties of water, such as its high boiling point and surface tension, and how they play a crucial role in stabilizing the structures of proteins and nucleic acids. This detailed explanation, couched in terms of electronegativity and electrostatic interactions, provided a far more sophisticated understanding of hydrogen bonding than previous descriptive accounts. Moreover, Pauling's book included many detailed worked examples, which clearly illustrated the application of chemical principles to solve practical problems. These examples covered a wide range of topics, from calculating pH values to determining equilibrium, constants to predicting reaction rates. He meticulously worked through each problem, explaining the underlying concepts and demonstrating the step-by-step procedure for obtaining the correct answer. These examples proved invaluable for students attempting to master chemical calculations. These specifics were absent from most texts available before. The lasting influence of college chemistry is evident in the continued relevance of its core concepts and pedagogical approaches. Even as chemistry continues to evolve, with new discoveries and theoretical advancements, Pauling's emphasis on electronic structure, bonding theory, and molecular geometry remains central to chemical education. His book serves as a testament to the power of clear, rigorous, and conceptually driven teaching, so much so that teachers may sometimes forget the novelty of the concepts, as these concepts seem to be the natural way to teach. In conclusion, Linus Pauling's college chemistry represents a landmark in the history of chemical education. Its emphasis on fundamental principles, integration of theory and experiment, and rigorous mathematical treatment transformed how chemistry is taught and understood. While certain criticisms and limitations led to revisions and alternative approaches, its enduring legacy is undeniable. The book influenced generations of chemists, shaped the development of computational chemistry, and continues to inform chemical education to this day. It stands as a testament to the power of a single, brilliant mind to reshape an entire field of study. He did this by not accepting the dogma of the time, and instead choosing to focus on explaining the world within the current understanding of physics.